When a production studio delivers a new 4K master file, it arrives as a massive 2 terabyte asset. To reach a global audience, that single file must be processed into roughly 1,200 unique variants and distributed across 190 countries. Viewers access this media through entirely different hardware and network conditions. A smart TV wired to a gigabit fiber connection requires a vastly different data payload than a cellular phone struggling on a 3G network. Processing a catalog of thousands of titles to meet these exact specifications sequentially creates an immediate computational bottleneck. Encoding a single high-resolution movie start to finish on a dedicated server takes over 24 hours. The engineering mandate is absolute. Ensure instant global data distribution at maximum quality for each device, without buffering, regardless of local network fluctuations. Meeting this mandate requires abandoning the traditional server-client model, where a central server pushes video to a user. Instead, the solution relies on a strictly decoupled, stateless microservice architecture. The entire system is strictly divided into 2 distinct halves, a centralized control plane and a distributed data plane. The central control plane manages transactional workflows, media ingestion, billing, search indexing, and all heavy, computationally expensive media preparation pipelines. The data plane is positioned directly at the network edge, localized within internet service providers. Its sole responsibility is the high-throughput, low-latency delivery of the final video files to end users. This strict physical separation is an operational necessity for system resilience. By isolating high-volume video streaming traffic from back-end transactional databases, a massive sudden surge in viewership only impacts the edge caches. The core ingestion and compute infrastructure remains completely insulated from the load. The digital asset supply chain begins at the ingestion boundary. This is the exact entry point where raw production masters enter the control plane for processing. The first step is a structural indexing process. The system scans the raw file to generate basic metadata and establishes frame-accurate byte offsets, creating a map that allows precise seeking within the media. Next, the file undergoes multi-stage parallelized validation. Workers scan the bitstream for spatial corruption, interlacing artifacts, and audio synchronization drift. If a single anomaly is detected, the automated pipeline halts the ingestion process immediately. Stopping at the boundary prevents the system from passing structurally compromised media downstream, saving highly expensive cloud compute resources from processing a corrupt asset. Once validated, the file faces the primary compute bottleneck. Because encoding a 2-hour master sequentially takes a full day, the file must be broken apart. The video timeline is sliced programmatically at group of pictures, or GOP, boundaries. This creates roughly 720 independent, self-contained segments, with no interframe dependencies crossing the cuts. These raw chunks are uploaded to cloud storage, and their individual transcoding jobs are posted as messages into a central Amazon Simple Queue Service, or SQS, bucket. A massive fleet of stateless worker nodes, operating on cost-effective ECT SOD instances, continuously pulls this queue. They fetch the raw chunks, execute the transcode according to a specified codec profile, and push the encoded outputs to a new storage bucket. This architecture is fault-tolerant by design. If the cloud provider abruptly reclaims a spot instance mid-job, the unacknowledged message simply reappears in the queue for another worker to process. Cloud monitoring tools track the depth of the queue in real time. As demand spikes, auto-scaling triggers elastically provision more worker nodes to clear the backlog, spinning them down when the queue empties. When all segments are processed, a final assembly service stitches the independent chunks back together, verifying timing structures to ensure frame-accurate alignment. By decentralizing the workload, a sequential 24-hour bottleneck becomes a highly parallelized background task completed in under 15 minutes. Historically, streaming providers applied rigid, static encoding profiles to all media, allocating the same bitrate to a complex action film as a quiet drama. This wastes massive amounts of bandwidth. Modern pipelines use content-aware encoding. Before transcoding, the system analyzes the unique spatial and temporal complexity of every individual title. Simple 2D animation contains low spatial detail and minimal motion vectors. The visual information remains largely static between frames, allowing it to compress highly while maintaining excellent visual fidelity at low bit rates. Conversely, a live sports broadcast contains high motion entropy and highly detailed textures. These complex scenes demand significantly higher bit rates to render sharply and avoid blocking artifacts. To evaluate these differences at scale, Netflix developed VMAF, a perceptual quality metric that programmatically assesses video quality based on how the human eye actually perceives it. This table maps out the custom encoding ladder generated specifically for an asset, dictating the exact optimal bit rates required for every resolution tier, from 4K down to 240p. Dynamically allocating bit rates based on scene complexity maximizes the visual quality delivered per bit. Across billions of hours of streaming, this optimization saves petabytes of global bandwidth. With the files optimized and stored on the edge servers, delivery shifts to the data plane. Modern HTTP streaming relies entirely on the client device pulling data rather than the server pushing a continuous feed. Before playback begins, the player downloads a manifest file. This acts as a map, outlining every available resolution variant in the encoding ladder and the exact location of each multi-second segment. To decide which variant to pull, the client relies on adaptive bitrate, or ABR, algorithms. The first approach is throughput-based decision-making. This equation uses an exponential moving average to estimate sustainable bandwidth. By measuring the physical transfer metrics of recently downloaded segments, it calculates a safe bitrate for the next request. The second approach relies on buffer-based algorithms, which ignore volatile network speed estimates entirely. This logic maps the player's physical buffer occupancy directly to the encoding ladder. If the cache of downloaded video drops below a critical safety threshold, the algorithm triggers an immediate request for a lower bitrate chunk. Modern hybrid players evaluate both throughput estimates and buffer trend indicators. They execute seamless quality transitions exclusively at segment boundaries, allowing the resolution to shift without interrupting playback. These algorithms offload the immense complexity of network adaptation directly to the edge devices. By dynamically sacrificing resolution before a buffer runs empty, the system guarantees continuous playback over unpredictable connections. While the standard pipeline operates within a flexible 15-minute window for pre-recorded media, live events shrink that buffer to a brutal 2-second real-time limit. To bridge the gap between live cloud encoders and the edge delivery network, the architecture relies on a specialized microservice known as the Live Origin server. The Live Origin operates under severe constraints. It demands extremely high write availability, where any write operation that takes longer than 500 milliseconds is classified as a critical system failure. During peak viewership, an Origin storm can trigger millions of simultaneous requests for the same segment. The system handles this by backing the Cassandra data store with a distributed write-through cache, while enforcing strict read-your-write consistency. This consistency ensures that the millisecond a segment is published by the encoder, it is immediately visible to the requesting player. If the data store resources become stressed, a priority rate-limiting system protects this live edge by intentionally dropping lower-priority DVR traffic. Ultimately, scaling live events requires replacing standard object storage with specialized database architectures that can guarantee this immediate visibility across millions of concurrent sessions. Looking at the fully assembled architecture, the path of a video asset traces a precise route from raw ingest validation through distributed SQS queues and EC2 workers, out to the edge network, and finally down to the client player. The computational bottleneck of video processing is resolved through stateless chunking, while the physical bandwidth constraint is managed by content-aware encoding and adaptive bitrate math. This scale is only possible because of strict physical isolation between back-end processing and front-end delivery. When an event draws 65 million concurrent viewers, that massive traffic surge interacts exclusively with the edge caches. The complex control plane pipelines remain completely undisturbed. Global streaming is achieved by dismantling the concept of a continuous video feed. It replaces it with millions of independent, stateless HTTP objects, dynamically pulled by intelligent clients at the absolute edge of the network.